In this video, we're going to work through the steps to validate a regression model using two common forecasting performance metrics, the mean absolute deviation and the mean absolute percent error. To accomplish this, we're going to generate forecast values using a linear regression equation that we found using Excel's regression tool and a set of training data. From there, we're going to use those forecasted values along with the original actual values of our dependent variable to calculate the mean absolute deviation and the mean absolute percent error values using both our training data set and a set of test data. It's important to remember that anytime you're developing a prediction model, it is a best practice to divide your data into both sets of training data and testing data. The training data is what you use to actually build the model and fine-tune it, while the testing data is a holdout sample that is used after the model is developed to measure its performance. To properly validate a forecasting model, it's common to calculate performance metrics on both the training and the testing data sets separately. This then allows you to compare how well the forecasting model is performing using data that it has previously seen during training and testing data that it has not previously seen. In the end, our hope is that the performance metrics between our training and our testing data end up being relatively close to one another, which indicates that our model is robust enough to estimate future instances at a similar level of performance, and our model isn't overfitted to the training data set. So let's go ahead and jump into this small example. So I have a regression model here that I've already built using some data on sports cars, where I had different independent variables that I'm using to estimate the top speed that those vehicles can hit at a quarter mile. Now I started off with a handful of independent variables, and through multiple iterations, I eliminated the variables that were determined to be statistically insignificant, and I also pulled out any variables that had issues with multicollinearity, meaning that they had high correlations to one another and were not independent. So now what I want to do is, using my final regression equation, which is right down here, I'm going to go ahead and calculate forecast values for my training data. And then down here, I have 4 records that I held out that I did not use to train the model. And I'm going to calculate forecast for those. So again, it's important to remember that with our training data, I fed the model both the X independent variables as well as the Y dependent variable values. And for my testing data, I did not feed any of this information into the model. So this is effectively instances that the model has never seen before. And when we calculate these forecasts, we're going to use the actuals to calculate some error metrics, mainly the mean absolute deviation and the mean absolute percent error. And then we're going to compare the results between training and testing. And again, our hope is that, well, we hope that the accuracy is very high, and we hope that the metrics for training and testing are similar or not significantly different from one another, because that means that our model is very robust. So what we're going to do here is let's start off by calculating our forecast for the training and the testing data. So what I'm going to do here is just build out my calculation. So I'll take the constant intercept here, and I'll add to that the coefficient for horsepower, and I'll multiply that by the value of horsepower for this record here, the first one. And then I will add to that my coefficient for the price, and I'll multiply that by the price value. Now I'm going to go ahead and change my references to these coefficients to absolute cell references, so that when I move this calculation down, all of those references go with it. And I can just double check here at the bottom to make sure that the references did in fact copy down properly. So once I have that, I'll go ahead and copy this formula here and paste it down for my testing data set and just confirm that, yep, all my references are correct. And this is really the value of using those absolute cell references. If you don't know how to do that in Excel, when you reference a cell, you just click on it and hit F4 on your keyboard, and it will add those $ in front of the column and the row, indicating that that reference is fixed. And so when you copy or drag that calculation anywhere here on the spreadsheet or inside the workbook, that reference stays fixed. So very quickly, using this approach, I can calculate all of my forecasted values for my training and my testing data. Now I want to start calculating out our error metrics. So the mean absolute deviation is a very common metric that's used to measure error when we have a forecasting model like this. And all we're doing here is we're taking the absolute value of the difference between my actual value for y and my y hat, or what's my forecasted value. And then when I calculate each one of these independently, that's the absolute deviation. And then at the end, I average them all up, and that gives me one number that is my mean absolute deviation. In the case of my mean absolute percent error, which is the other metric we're going to calculate, it's very similar. We calculate that absolute difference between the actual and the forecast, and then we scale it by dividing it by the original actual. And this makes it easier for us to, if you, for example, took the same model and applied different data to the model, like you wanted to try to forecast different things in different units, well, the mean absolute deviation alone makes it very hard to compare the performance of that model across different scales or different units. But the mean absolute percent error normalizes this. So they're really good to use together because they give a full picture of basically the performance of our model. So what I do here is I'm going to use the ABS, which is the absolute value function here in Excel. And I'm simply going to take my actual, which is the Y value here, and I'm going to subtract the forecasted value for each one of these records. So I'll just write this function once here, and I'm going to copy it down. Note that I'm using relative cell references here because I'm just copying it down here. And we'll do the same thing for our test data set. I'm just copying it down, making sure the references are updating correctly. And then what we'll do is we'll just take our average here for the training data and the test data. Now, once we have those numbers, we can see that they are relatively close to one another. And what I mean by relatively close is they're not wildly different, right? So here, my error is 1.73, which is, rounds up to 2. And then here, 2.3, which rounds down to 2. So they're pretty close to one another. If I had errors down here that were, 10, 20, 30, whatever that might be, really big differences between my testing and my trained data, that would definitely be problematic. And the mean absolute percent error is going to give us the perspective of the scale of the error. So what we're going to do here is we're just going to take the absolute deviation calculation we had for each record, and we're going to divide it by its corresponding actual. And that will effectively convert this error term into a percentage. And so we'll do that for all of the records here. And again, using relative cell references, I can just copy this down. And then again, I can find the average. And here, since I used relative cell references for this average calculation, I should be able to just copy this over. And it works there. So we'll just copy this over there as well. Now I'm just going to quickly convert this to a percentage using Excel's percent option here. And so we can see that for our training data set, it's essentially 98% accurate if we round 1.72 up to 2. And for our testing data set, our forecasts are around 97 or 98, somewhere in that ballpark. They're very, very similar. So what this tells us is that our model, using data of a similar type, is going to be robust to future instances. So if I wanted to predict the top speed at a quarter mile for other vehicles, I could type in the horsepower and type in the price, and I should expect a pretty good accuracy here. If these are yielding a high 90s accuracy for future instances, really anything above 90% is going to be fantastic. And I can tell here, since the difference, there's not a big difference between the training and the testing metrics, that also tells me that my regression model was not overfitted to this original training data.